So in this lecture, I want to look at halogen substituents on aromatic rings for electrophilic aromatic substitution reactions. It turns out that halogen atoms are sort of a mixed bag between what we've been looking at. They are, first of all, consistent with what we were looking at last time, OrthoPara directors, but they're also deactivators of in EAS reactions, electrophilic aromatic substitution reactions, which this combination is unusual. Now, for the most part, what we'll see is that deactivators are generally meta-directors. Deactivators are generally meta-directors, okay? But they aren't the case now. So we'll focus on halogen going forward. So it turns out that if we ask the question why this is the case, we'll start with why are halogens deactivators? Well, it turns out that halogens are the most electronegative elements on the periodic table. Okay, just a fact. We've seen that for a while now. That, you know, we could draw a mini periodic table with an O and then an entire group 7. So there's fluorine, chlorine, bromine, and iodine. So they're furthest to the right in the periodic table. And in fact, if you look at the numbers for these, they beat out everything to the left of them, even down to iodine, right? So I know you're supposed to go up and to the right for more electronegativity, but it turns out once you hit group 7, they're all just super electronegative. Okay, so if they're more electronegative, they withdraw electron density using inductive effects. Or by way of inductive effects. They don't really use them. They just take advantage of them. This is how they do their job. Okay, so that's the important takeaway here is we're going to withdraw electron density from the aromatic ring by way of inductive effects because the halogen atoms are so electronegative. They're polarizing the bonds. They're taking them away so strongly. And we can kind of draw a picture for that. Halogen atoms are deactivating due to electronegative due to being so electronegative. I guess that's a bit redundant. So electronegative, which tells us that we have inductive effects. Now, if they're deactivating, that reminds us that these things are withdrawing groups. So I just, sorry to be so redundant. I just want to emphasize halogen atoms are deactivating. They withdraw electron density by way of inductive effects, and that slows down the reaction in an electrophilic aromatic substitution reaction. Okay, they're not great things to have present if you want to try to do an electrophilic aromatic substitution reaction. We'll see slower reactions than we would see with benzene by itself. So reacts less efficiently than benzene in EAS reactions. Okay, it's just kind of what happens. Now, what's kind of weird, and I know we haven't looked at withdrawing groups yet, so we haven't really seen meta directors yet is that halogens are OrthoPara directors. So why are halogen atoms OrthoPara directors? OrthoPara directors. The answer is resonance. So like the oxygen atom, we're going to see competing effects from resonance and inductive, sort of. Yeah, I mean, in reality, they are. So it turns out the resonance effects compete with inductive effects. Okay, let's look at that. If it's resonance effects, that means we can draw resonance structures. Well, we can, okay? We can have our X group. Now, X is going to have 3 lone pairs of electrons. We can push electrons into the ring by resonance because the electrons are delocalized into the pi system, pushing a negative charge here. Now, we've done this resonance description before, just not with a halogen atom. We have charge separation. We have a second best resonance structure, but we put the negative charge on the ortho position. That tells us right away that ortho products will form. We can push the negative charge through to the para position. That's going to tell us that para products can form. But we never push that negative charge to the meta position. Rather, it circles around and gets back to an ortho position before neutralizing the halogen atom. So we see more reason why ortho products can form, because we can put a negative charge at the ortho and para positions of our benzene ring. And so what that means is if we take this same molecule and we react it with some sort of super electrophile in an EAS reaction, I'm just going to have E plus, put EAS over the arrow, which means we're going to lose a hydrogen atom. What we'll get then is, based on these resonance structures, we'll get substitution at the ortho position, which is the same on either side, by symmetry, and the para position. Ortho and para products are formed. Okay, so that's going to explain to us why we are going to see reaction at the ortho and para position. But here's the deal. This reaction is still super slow. It's sluggish, it's not efficient, and that's because X will deactivate the ring. Okay, just a second. Last time you said when the oxygen was present, we had inductive effects that were withdrawing, just like what we're seeing now, and resonance effects that were donating and led to the ortho and para products. Now, not only were they donating, but that lone pair being popped into the ring system meant that kind of taught us that resonance effects will beat inductive effects for the most part. Yes, for the most part. There's that one exception. That one exception is when the X is the substituent is so electronegative. So this thing is so strongly electronegative. The bond between carbon and halogen is so polarized that we see a very strong dipole. And in this case, this very unusual case, this very strong dipole withdraws electron density so strongly that it exceeds donation by way of resonance. Okay, so the lone pairs going in tell us where the product, the electrophile is going to add, but it's the substituent pulling electrons away that tell us why the reaction is so slow. So halogens are just slow because they're so electronegative. Now, when I say it wins, it doesn't mean that it's like completely turned off. It turns out that halogen substituted benzenes can do this reaction not so bad. It's a little bit slower than benzene, but it's not so bad. And that's because we have the resonance effect trying to pick up steam a little bit and negate or attenuate or kind of stop and shield the withdrawing effects felt by resonance or inductive effects. So the resonance effects are trying to hold their own against the inductive effects. Usually they win, except in the case of halogens, because halogens are so strongly electronegative. Okay, so I'll do it for halogens. It's an unusual case where we have a deactivating group directing OrthoPara. As we'll look at when we get into electron withdrawing groups where they have a resonance contribution that pulls electrons away, we'll see there's no chance. There's no chance for OrthoPara products. And so if we have to have products formed, they go to the meta position. And so they're often called meta directors. Okay, so that'll do it for this one.